Hello people. Welcome to this playlist on Python for data science. It is a vast domain where a plethora of libraries are used. The most commonly used libraries are NumPy, Pandas, Matplotlib, Seaborn, etc. In this series, we shall be diving deep into the basics, purposes, and the workings of these libraries. First up, NumPy. NumPy is the fundamental package for scientific computing in Python. It is a Python library that provides a multidimensional array object, various derived objects, such as masked arrays and matrices, and an assortment of routines for fast operations on arrays. These operations include mathematical, logical, shape manipulation, sorting, selecting, input or output, discrete Fourier transforms, basic linear algebra, basic statistical operations, random simulation, and much more. It is tough to find a scientific library that does not depend on NumPy. At the core of NumPy is an ND array. It is short for n-dimensional array. An array is a data structure that stores multiple elements of the same type in a contiguous block of memory. Unlike lists, which can grow dynamically, arrays are of fixed size when created. Any modification to the size of the array would result in the deletion of the array and creation of a new array in its place. Though lists and arrays are collections of elements, there are quite a few differences between them. First of all the elements in the array must be of same data type. A list does not have this restriction. A list can grow dynamically after its creation, but an array cannot. Arrays are more efficient than lists in terms of computation and storage. Computational efficiency comes from vectorization. Memory efficiency comes from having no overhead for dynamic resizing. Why is NumPy so popular? Images, videos, and audios can be represented as NumPy arrays. For example, let us take the very video you are watching. It is a 1920 by 1080 pixel video. It can be represented as a series of frames, where each frame is a NumPy array of 1080 by 1920 by 3 elements. 1080 is the height, 1920 is the width, and 3 denotes the color channels, red, green, and blue. Each element in this array has a value between 0 and 255. Normally, in digital photography, width comes first and height comes second. But as NumPy arrays are row major, height comes first and width comes next. Note that it is just a different standard of representation, and it does not distort the shape of the media. Not just in media, NumPy is used in places where computational efficiency and speed is vital. How does NumPy achieve this efficiency? Through a couple properties called vectorization and broadcasting. Vectorization refers to the process of simultaneous application of an operation over all the elements of an array. This is achieved by offloading the calculations to a C language backend, where computation is much faster. In hindsight, we get the best of both worlds, the speed of C language and the concise syntax of Python. Let's compare looping and vectorization, shall we? Here is the problem statement. Calculating the sum of squares of first 1 million natural numbers. Clearly, there is a formula that can calculate the squares of first n natural numbers, and that is much faster. But, for the purposes of demonstrating the advantages of vectorization, we are going to do this without using the formula. The looping takes about 0.0856 seconds, while the vectorization method takes about 0.0044 seconds. This is a single trial, and the numbers may vary slightly, but it is clear that vectorization is way faster. Broadcasting refers to the ability of NumPy to deal with arrays of different shapes. Of course, some constraints have to be satisfied before the broadcasting is done. For example, when two arrays are being added, the shapes of the two arrays are compared, starting from the rightmost dimension. If the corresponding dimensions of the two arrays are equal, or if one of them is equal to 1, then the constraints for broadcasting are deemed to be satisfied. Let us look at this example. Here we try to add two arrays, but their shapes are not similar. One is a two-dimensional array of 2 by 5 shape, while the other is a one-dimensional array of length 5. During broadcasting, the shape of the smaller array is padded with ones until both the arrays have same number of dimensions. Note, no actual change is being done to the array. Just for comparison, the tuple of dimensions is being padded with ones. Now, from the right end, the corresponding dimensions are compared. Rightmost dimension matches 5 and 5. Then, moving left, we compare the dimensions 2 and 1. They are still compatible, because one of the dimensions is 1. Hence, the broadcasting rules are satisfied. Now, the addition happens element-wise, and the second array is added to the first array by its replication along axis 0. In a two-dimensional array, the rows are axis 0, and the columns are axis 1. Now that we know what arrays and their advantages are, let us start working with them. There are lots of ways of creating an array. We can convert a list or a tuple into an array. We can use the arrange method, or zeros, or ones, or empty method. We can read from a disk, convert raw bytes from strings or buffers, etc. Let us look at some examples of these, one by one. Lists, or tuples, can be converted to arrays by passing them as arguments to the array method. A simple list will be a one-dimensional array. A list of lists will be converted into a two-dimensional array. Further nesting will increase the dimensions correspondingly. So, in general, any array is called ND array in NumPy. When printing the array, firstly, the rightmost dimension will be printed from left to right. In this case, the innermost of tuples of length 3 is the rightmost dimension. Notice that they are printed from left to right. The last but one dimension is printed from top to bottom. Here, it is 1, 2, 3, and 4, 5, 6. All the other dimensions are printed from top to bottom as well, but there is an empty line demarcating the dimensions. Let us look at some array attributes while we are at this. The type attribute gives the data type of the elements in the array. The item size attribute gives the size of each element in bytes. Note that both data type and item size are common for all the elements in the array. We can also obtain the number of dimensions and the shape of the array from ndim and shape attributes. There are quite a few functions in Python that we can use to create arrays from scratch. We can create one-dimensional arrays using arrange and linspace functions of NumPy. Arrange works similar to range iterator. Linspace is used when we need a specific number of equally spaced values between a lower bound and an upper bound. While arrange excludes the upper bound, linspace includes the upper bound by default. However, this behavior can be changed as well. The eye and diagonal functions can be used to create identity matrices and diagonal matrices respectively. These are helpful in linear algebraic operations. While the functions discussed above create arrays in strictly set dimensions, there are a few functions which can create arrays in any shape. For example, the zeros function creates an array of specified dimensions and sets all the elements to 0. Ones does the same, but it sets all the elements to 1. Empty creates an array of desired shape and with uninitialized values. We can also create arrays out of random numbers. While the default data type of an array is a 64-bit precision floating point, you can explicitly specify the data type using the dtype parameter. We can store arrays to disk and retrieve them using standard formats like NPZ and NPY. We can also load arrays from the data in text files, CSV files, etc. NumPy is also used by libraries such as Pandas, TensorFlow, scikit-learn, OpenCV, etc., which are commonly used in machine learning. They create, manipulate, and perform operations on arrays to make their processing faster. Let us look at some of the basic operations. Sorting an array is simple with the sort function. You can specify the axis, kind, and order when you call the function. The kind parameter takes in the type of sort, like heap sort, or merge sort, or quick sort, or stable sort. There are some variants of sorting. Often used is argsort, which returns the initial index positions of the elements after sorting them. There are some other variants like lexort, search sorted, and partition. The order of sorting can be specified as well. Let us look at a couple examples. The first example is a case of simple sorting. NumPy does not give an option for sorting in descending order, but the sorted list can be reversed easily using the Python reverse syntax, ::-1. The second example demonstrates the usage of order. Here we define a two-dimensional array, not unlike a table. We have the names of the Knights of the Round Table, along with their height and age. We can explicitly give names and data types for each column. The names could be used in the order parameter to tinker with the sorting. Can we reshape an array? Of course, we can. We can convert one-dimensional array into higher dimensions, or n-dimensional arrays into one-dimensional arrays. We can achieve this using reshape, newAxis, or expand-dims functions. In the first example, we have converted a one-dimensional array of 8 elements into a two-dimensional array of 2 columns and 4 rows. The second and third examples achieve the same result. In the case of newAxis, we specify where to insert the new axis, using np.newAxis, but in the case of expand dimensions, we specify which dimension to expand. Notice that there are 2 square brackets in the expanded arrays, while in the initial array, there is only one. This means that a one-dimensional array has been converted into a two-dimensional array. NumPy supports slicing and indexing, just like in Python. We can pick specific elements by providing the index position inside square brackets. The same has been demonstrated in the first example. In the second example, we have an array, and we filter the elements based on a condition. Here, we filter for elements less than 5, and a new array with elements less than 5 are returned. Actually, behind the curtains, the conditional expression returns a Boolean array, which when applied on the original array, returns the elements whose corresponding values in the Boolean array are true. We can stack arrays vertically or horizontally using vstack and hstack functions respectively. We can also split the arrays vertically or horizontally using vsplit and hsplit functions. The hsplit example splits the array into 2 equally sized parts, horizontally. The vsplit example splits the array into 3 equally sized parts, vertically. We can perform a variety of arithmetic and statistical operations on arrays. While most of these operations are available as NumPy functions and array methods, some of the operations are available only as functions. For example, median is available as a NumPy function, but not available as an array method. Addition, subtraction, multiplication, division are supported. We can also quickly get the sum, product, mean, standard deviation, etc., using the appropriate methods. Sum, product, median, and other statistical operations can be performed by passing the array as an argument to the respective functions of NumPy. N-dimensional arrays can be transposed using transpose method or the t-attribute. Arrays can be reversed along any dimension using the flip function. Since NumPy does not have an explicit way to sort the arrays in descending order, we can use this function on the sorted array to get an array sorted in descending order. In this example, we can see the array reversed along its 2 axes. If the axis parameter is not provided, the array is flipped along all its dimensions. We can remove the duplicates in an array by using the unique function. It is also possible to get a frequency distribution of the values by setting the value of return counts parameter to true. It is set to false by default. This example demonstrates the presence of 3 1s, 2 2s, and 1 3 in the original array. We had earlier seen an example where a one-dimensional array was transformed into a multi-dimensional array. The converse is also possible. This is achieved by using the flatten and Ravel methods. Both of these methods transform the array into a one-dimensional array, but the difference lies in whether the parent array is affected or not. In the case of flatten, the parent array is not affected. Notice that the item assignment affects only the flattened array, and not the original array. The Ravel method functions similarly, but the original array is also affected. Notice that the shape of the original array stays intact, but the item assignment has modified the values in the array. That brings us to the end of this video. Today, we learned about the applications of NumPy in numerical computing, linear algebra, image processing, statistical analysis, and so many more. We also learned that vectorization and broadcasting are the powerful techniques that give NumPy its speed and efficiency. We also looked at some of the functions and methods. For more tutorials, like, share, and subscribe. Don't forget to hit that bell icon. Until next time, happy learning!